Good morning, everyone. Welcome to the new episode of Science with QuEra. Today, we will focus on an important topic for quantum computing with neutral atoms, which has to do with a new platform for integrated photonics. The content of this presentation today is based on a recent work that has been published on the arXiv in August of this year. That is the result of a collaborative approach with the Sandia National Labs, MIT, and the University of Arizona, with funding from DARPA and AFRL. My name is Tommaso Macrì. I'm Senior Director of Business Development at QuEra Computing, and I'm honored to be joined together for this presentation by Noel Wan, a photonics scientist that was the senior author of the presentation that I just highlighted. Thank you, Noel, for being with us.
Thanks so much.
And by Anshuman Singh, a senior photonic engineer at QuEra Computing. Thank you, Anshuman.
Thank you, Tommaso.
And the presentation will be structured mainly in three parts. At the beginning, I will start providing some details about QuEra technology, about our approach to quantum computing by using neutral atoms. We will add then, in the second part, a number of important technical description of the problem of integrated photonics that will be delivered by Noel and Anshuman respectively. And at the final part, we will probably respond to some of your questions and give some thoughts regarding the presentation and some potential updates regarding some recent work that we've been doing at the company. So with this, let's move directly to the first part of the presentation. Let me tell you very briefly about QuEra. QuEra is considered by many the scientific and commercial leader in neutral atom quantum computing. We started our journey back in 2019 together with Harvard and MIT, and we advanced together to this day the technology that we are developing at the company. Our systems are already available both on premises and on a major public cloud. We're working very closely with AWS Bracket, which is a service from AWS providing access to several modalities of quantum computing. Our headquarters are in Boston, Massachusetts, but recently we also opened offices in Tokyo, in Japan, as well as at Harwell in the UK. We are very well funded, and our technology is trusted and supported by major organizations such as Google, SoftBank, and NVIDIA. The platform that we are focusing on is called neutral atoms. We use what are called nature's perfect qubit. In particular, for the platform that we are developing today, we use a specific atomic species, which is called rubidium 87. That displays many important features in terms of the opportunity to scale these systems to several hundreds of thousands of qubits without the need of really interconnecting different QPUs, different quantum processing unit. At the same time, there are some specific capabilities, and during the presentation, we will highlight some of them that will make the system particularly relevant for some early demonstrations of error correcting codes. Another important feature from the point of view of the architecture and its engineering is related to the absence of complex cryogenics that actually for us allow us to have a relatively small footprint and low energy consumption of our hardware. The first machine that we put on the cloud back in November 2022 is called Aquila, that is now available on AWS Bracket for more than 130 hours per week. It is a system that works in the so-called analog mode with up to 256 qubits. It's a system that is currently very widely used. With this, we really help HPC centers, enterprise innovators to start working on specific use cases, and governments to put together programs that will provide access for training and early use of quantum computing systems to a wide audience of researchers and related stakeholders. This is, of course, not all we have to say. Recently, we also installed our second generation quantum computer, which is called Gemini, which is the first commercial gate-based neutral atom quantum system integrated in a supercomputing center. The system is really ready for demonstrations with quantum error detection and quantum error correction. And it has been installed at AIST, at AIST in Japan, right outside of Tokyo, in an effort that to basically combine both quantum computing capabilities with classical supercomputing ones. There is also very close, this is also a very close collaboration with NVIDIA, which is one of our the closest strategic partners. So with this, I would like to give the floor to Noel to start diving deeper into the technical part and focusing first on this problem of local addressing. Noel, the floor is yours. Feel free to start sharing your screen. Maybe while you start share your screen, I would like to also to advertise to our attendees that there is a Q&A window on Zoom. We are very happy to take your questions, both during the presentation as well as during the final part of the discussion today. Please, Noel.
Thank you, Tommaso. So I'll be going through first the basics of how quantum computing with neutral atoms work. So I think the takeaway from this slide is that almost all the control that's implemented and also needed to execute useful quantum algorithms on such quantum computers is all done optically. So the three basic blocks of doing quantum computing with neutral atoms are for atoms, which are our qubits, optical tweezers, which are used to move individual atomic qubits simply by moving the laser tweezers, and also by laser gates. So we also use different laser frequencies to effect logic between atoms. So in our case here, we are using the Rydberg states to enable logic between separated atoms. So this here is a high-level diagram of basically how a neutral atom quantum computer works using a variety of optical devices and so this is the Gemini class quantum computer that Tommaso was briefly mentioning earlier, and this was work done in 2024, published early this year using the Gemini quantum computer. Here in this video, you see all that three basic blocks in action. So every spot here is an atom, a rubidium atom. And you can see that by moving lasers, we can actually move atoms around. And by placing atoms close to one another and turning on lasers in a precise way, we can execute quantum algorithms on this quantum computer. So the photonic challenges for quantum control of atoms are quite unique. So first of all, I'd like to highlight that quantum computers based on neutral atoms are scaling very rapidly. Just this year, two very exciting results have shown that now quantum computers with neutral atoms are entering into the thousands of qubits level. So here showing a 3,000 continuously operated quantum computer, and here a quantum computer with over 6,000 very coherent atomic qubits. And so now the question is all about how do we scale optical control? And first we have to realize that the parameter space that we are discussing here is rather complex. So first of all, there's the aspect of scale. There's thousands of qubits needed to realize fault-tolerant quantum computing. But also there are aspects such as enabling independent control. How do we scale optical systems without scaling the laser technology in a rather naive way, right? Because here we will have many degrees of freedom, and that translates into the control of essentially the laser technology. But this photonic control also has to be has to span quite a large range of timescales. First, we need that some gate times may be 10 nanoseconds, and some gates may be 10 microseconds. So the photonic control technology has to be adaptable to these various timescales, and as well as the wavelengths. So the wavelengths in a typical quantum computer may span from the UV all the way to the near IR telecom band. And as you all know, most of the optical control technology has been developed primarily for telecom applications, which is in the band of 1300 to 1700. So having to meet all these challenges is really the one of the central goals in engineering photonic systems for quantum control of atoms. To take a closer look at what goes into this light control, it's like the three prototypical examples that we'll highlight is the spatial light modulator, or SLM, the acousto-optic deflector, or the AOD, and photonic integrated circuits, or PICs. So first, and all these serve different purposes as in the quantum computer, as we'll show. So the spatial light modulator is an incredibly powerful technology that enables us to do flexible addressing and trapping of atoms. It has synchronous grid addressing. However, it's a bit too slow for doing gate operations, as the relevant timescales is on the order of milliseconds. On the other hand, acousto-optic deflectors are much faster than SLMs with timescales on the order of microseconds. However, they have asynchronous row addressing, which prevents them from being completely independent in control, unable to achieve independent control. And scaling this to beyond several rows will run into challenges of nonlinearity and inhomogeneity. Photonic integrated circuits, on the other hand, are faster, even faster than AODs. Some PICs can go below the nanosecond switching timescales. And it's highly scalable in the sense that it can be manufactured in the same foundries that are used to manufacture our chips today. However, because these are lithographically defined systems, they may have long development cycles, and you need to know in advance what you're trying to print on the chip and before receiving such chips and going through the test and development cycle. So we'll discuss one development that we've been pioneering here at QuEra together with our partners, and that's try to use PICs and developing PICs to the level that is compatible with fault-tolerant quantum computing with neutral atoms. So we designed photonic integrated circuits and have it manufactured at Sandia National Labs in this work. And shown here is an 8-inch wafer, not too different from the silicon wafers that we are used to seeing. And this technology is based on silicon nitride, which is transparent from blue to the infrared spectrum of light. And here we can see in this platform, we have integrated aluminum nitride, which is a piezoelectric material. And by applying voltages to this layer, we are able to actuate the silicon nitride waveguide that is above this layer. And if we design the system correctly, this amounts to executing a phase shifter on or imparting a phase shift on light propagating in the waveguide. So here we are showing our architecture. So we design a Mach Zehnder interferometer switch array to perform intensity switching of light. And by sending in voltage pulses, we are able to turn on and off such array of switches. And so here we are showing that by coupling just one channel of light into the chip and having passive photonic networks that go through this MZI switch array, we are able to execute some sort of optical gate array highly in a scalable way. And this would be delivered to the atoms in our quantum computer. So I'll discuss our very exciting results here. First, we've demonstrated that across the entire die at a wavelength of 795 nanometers, which is the wavelength needed for single qubit control, that we consistently achieve extinction ratios, which is which characterizes how much leakage there is in the system, consistently below 70 dB. So we are able to turn on and off light with over 10 to the power of 7 in dynamic range. So this represents a one of the most advanced extinction ratios ever achieved in the photonic integrated circuit platform. At the same time, we also demonstrate that we can do this at a wavelength of 1030 nanometer and at a wavelength of 420 nanometer. And these two wavelengths are needed for doing 2-qubit gate on rubidium atoms. So we're very excited to see that the switches that we've designed into our system is consistently high performing and meets the requirement for performing high fidelity gates on atoms. In addition to the high fidelity control, we also want this the light control to be extremely fast, because the time scales vary from tens of nanoseconds to microseconds for different operations in a quantum computer. So here we show that we can achieve the optical response of our device is on the order of 30 nanoseconds for all wavelengths. And we can achieve dynamic switching, starting from an on state to an off state, to over 60 dB in a matter of in steady state switching in order of about 1 microsecond. Next, for executing deep quantum circuits, you want this system to be passively stable over long times. So what we are showing in figure C and D here is that the pulse area standard deviation over milliseconds of time over the millisecond time scale is below 0.1%. So from shot to shot, the area under the curve of the laser pulse is 99.9%. And we show that we are able to maintain this performance over very extended periods of time of over 500 microseconds, over 500 milliseconds. Next, I'll turn over to Anshuman, who will tell you about how we use this in a quantum computing architecture.
Thanks, Noel. Let me share my slide quickly.
Maybe while Anshuman shares the slide, there is a question from one of our attendees. Noel, would you like to take it? What is the power damage threshold for a single channel and for the global input? You are muted.
Yeah, so that's a very good question. Thank you for this interesting question. So we've characterized the device at near infrared wavelengths, and we found that we can insert or couple in more than 1 watt of optical power without damaging the system. We have not fully pushed it to the limit, but we know for sure that we can operate at above 1 watt optical power.
Very good. Anshuman, please, the floor is yours. Thank you, Noel.
Yeah. Thank you, Noel. Thank you, Tommaso. So yeah, let me walk you through this big atomic qubit interface. So far, I believe Noel did a very good job explaining the local addressing issue and how the PIC can come to the rescue. So if I can summarize what we have so far, we have shown or demonstrated the 8-channel device, a PIC device with a record performance. Extension goes as high as 70 dB, and the very high speed switching around 30 nanosecond with a stable pulse operation. And in addition to this comes with a very broadband operation going from visible to near infrared. So what I show here in the bottom left is this PIC chip with the 8-channel and gives a 8 spot. So what we would like to do next is to take this chip and plug it into our quantum processor, which are our atomic qubits. The question comes, what do you need in between? Do you need an interface or some kind of adapter? So this is what I will be discussing in next couple of slides. So on the left-hand side, you have this PIC chip again, and on the right side is this our quantum processor unit, our QPU. And at the core of this QPU is this our atomic qubits. So this is the grid of the atoms, and ideally we would like to have our PIC to talk to this atom in a very coherent way. So we need some kind of delivery or beam delivery system which can make the PIC output compatible with our QPU systems. So in short, a beam delivery module arranges the peak output according to the needs of the GPU. And in most of the cases, going from a 1D array of beam spots to a 2D grid. And since atoms are very sensitive to anything, so beam quality has to be supreme. So nice Gaussian beam and intensity very uniform across all these spots with a desired polarization and very low crosstalk. That means the influence of one spot at the position of the other spot has to be very, very minimum. So this is the characterization we did, and we take a small step first. So first we did a one-dimensional characterization of our beam delivery setup. So for that, we take like a fiber array, which acts as an interposer to give us a desired mode density. So in our case, the mode density is defined as the pitch between the spots over the mode field diameter. And this number is roughly around 5 in our case. So what you see is the image of our coming out of from our beam delivery system, nice Gaussian beams with a very nice defined, polarization and the, very low crosstalk. So the way we measure the crosstalk is in such a way as shown here. So let's say you take a very small detector and scan across all these 8 beams. So what you get all these 8 peaks, which is, understandable, and you do a second scan. And in that second scan, what you do, you switch off the alternate beams, like shown in the figure B here. And what you observe here, that at the position of the missing beam, there's still some signal. So that's actually leakage of the, the beams which are on at the position of the beams which are off. So that's define the level of the crosstalk. And in our case, the crosstalk level is around 50 dB, which is still a very good number. So if I can give a perspective, so that from the peak, we have a 20 dB extension, and now it comes to the beam delivery, and you get the contrast between the on and off around 50 dB. So that's the number we have right now for the crosstalk. So actually with that, we come to the end of our technical part, and I would like to give some final thoughts and not repeating the numbers I just said or what Noel said, but give you some key takeaways that the silicon nitride based piezo optomechanical system is really scalable because of its CMOS compatibility, and the demonstration of the performance we just shown actually allows us to scalable solution for the controlling the local qubits on the atomic qubits. So right now what we have is the 8-channel module, but we want to scale like in steps. So going from 8-channel to 64-channel into hundreds and thousands of channel. But when we do that, we also have to think about not only it's not only about fabricating these devices on the chip, but also has to think about the control system of these devices, and of course the beam delivery and how it interfaces with the atomic microscope. So I think with that, I would like to conclude and say thank you for your attention and give it back to Noel or Tommaso if you have any final remarks.
Thank you, Anshuman. Thank you. I would like to finish by thanking, first of all, you, Anshuman, and Noel for the great contribution to this presentation. Again, our collaborators that you see here at the bottom, and DARPA and the FRL for the funding of this work. I posted on the chat as well my email address if you have any additional questions, curiosities, or if you would like to be connected with our technical team developing the core technology that has been discussed today. I see that there are some additional questions. We will stay on the call for a few more minutes to respond to your Q&As. I hope that this webinar has been of interest to you, and thank you so much for your attention. And thank you, Anshuman and Noel, again.
Thank you.